see what gets on this.
Oh, yeah. So, Professor Morse, can you see the screen?
Yes, I can.
Yes.
And Chrissy, can you see the screen?
I can.
Okay, and I've sent you the presentation just in case if the presentation is not visible, you can open the presentation from there.
Okay, sounds good.
Sounds
I'll
good.
start my presentation. So hi, my name is Mayank. Welcome to my incredible 1.5 years with this project. I have tried to summarize my presentation in 40 minutes. I might have missed a lot of details, so I'll be happy to answer any question which you might have. So the project which I was working on is experimental and numerical simulation of borosilicate glass on split Hopkinson pressure water test. So let's get going. So I'd like to thank my advisors first. I would say these professor, because of these professor, I was able to incorporate a lot of materials in my research work. So I was able to incorporate the dynamics of material, experimental stuff, and simulation stuff. So I'll start off by thanking Professor Odegaard for giving me such an exciting opportunity to work on this project. He gave me flexibility to work on my ideas, as well as certainly keeping me on path. I'd like to thank Dr. Morse for always being there in my presentation, helping me out like what should be the next step, how should I carry out. He challenged my views that made me think out of the box, and I really enjoyed working with him. I'd like to thank Dr. Miskiaglu for teaching me how to do split Hopkinson pressure water test. I kept on breaking his instrument and he was very calm about it. So yeah, so I'd really like to thank for him giving me the keys to the lab. I really had an amazing time there doing the work, and I felt that I have actually contributed to the scientific community. So this project is under US Bureau of Reclamation. So Chrissy is holding the, Chrissy is the representative from that side. So so we always have like a bi-weekly presentation for this project, and she has been helping me out like what exactly is the requirement of USBR, how should we move about it. So it has been great working with her, and I kind of realized that what things I should work if there is something, if there is a work I'm doing on a presentation. So this is how the flow of my presentation would be. So I'll start off with like what is the background of the presentation, what is the background of the work. Then I'll move on to the dynamics of glass material, the experimental work, the simulation work, and some of the recommendation for future work. And then I'll go to the conclusion. So first we'll start off with the background of this project. So as you can see, this is the supply chain of the transmission line what we have. So what happens is the power is generated here and it is stepped up in this transformer. The transmission line is, the high voltage is ensured in this transmission line, because by that way the transmission loss is minimized, and there is a transformer which steps it down. So there are bushing like this which ensure that the that it is placed properly, it is guided properly, as well as for the safety of the power lines. So because of the functionality of this transformer, it has to be placed in somewhat height. So what happens is it is susceptible or it is viewable from long distance. So what happened in California was, again stuff. Can somebody help me with the change? So what happened in California was, so some of the nuisance creator, what they did is they were targeting the bushing. So what happened because of this, that there was a blackout, as well as because of the firing of the bullet, there were cracks in the glass, which kind of impacted the equipment around it. So to bring it back to the function, it took around 1 year for the power grids to bring it back to the function. So the whole point of US Bureau of Reclamation, this research was to create a defense mechanism for this bushing, so that it doesn't, if there is a bullet impact, it doesn't impact the other surrounding element. Next. So what USBR did is it conducted a test. So this is the setup of the test which was conducted. So there is a cylindrical setup, and the glass which is used is borosilicate glass. It had the provision of pressurizing internally, and there was a 0.22 caliber bullet which was fired, and this whole thing was viewed from a high-speed camera. So as you can see, these are the pictures what we got from the high-speed camera. So the top 4 photographs is for the no pressure, and the bottom 4 photographs is for the 100 psi. So I'll show you a short animation like how actually it would have looked if there was a bullet impact. So this is how it would be breaking. So it might show like how it might be happening for a zero pressure. So as you can see, there are fragments flying, and these are the fragments which were kind of impacting the equipment around the in the transformers. And this might be assumed for like higher pressure, which is zero atmospheric pressure. So this is how it looked. Next. So now I'll talk about like these were the 3 observations which were drawn from the photographs what we have from the testing. So as you can see the crack orientation. So what happened is just on the impact of the glass, there was a crack formed throughout the glass, as we saw in the animation as well. And it was radial in the impact zone, and as we move away from the impact zone, it was vertical and horizontal. The damage form was instantaneously on crack, and the size increased as we move away from the impact zone, as well as we increase the pressure, which is you might not see the lower, it is for the 100 psi. So more number of cracks were generated for that simulations. So the whole idea was that if USBR would have worked with these kind of tests developing a countermeasure, then it would have taken a lot of time as well as money to have any countermeasure. So what was suggested is to do FEA. So by FEA we could design the countermeasure, as well as the computing cost would be the cost which would be implying would be really less. Next. So what was done is an FEA model was developed. So for developing the FEA model, as we have seen, the geometry of ceramics is kind of complex. So the model was simplified first, the mesh size and mesh pattern were decided, and the failure criteria was chosen. So 2 of the people had worked before me, Sandesh Gandhi and Vijay. They have done incredible work in deciding on the mesh pattern which should be selected. So this is how the mesh pattern looks like. So this is the work from Sandesh Gandhi's report, and this is the mesh size which was selected. The failure criteria which was chosen was maximum principal strain. So what was done is the tensile strength was taken and maximum principal strain was calculated. So based on that, based on that calculation, the maximum failure principal strain came out to be 1.094 into 10⁻³ . So when this value was fed in the simulation by the people who were working before me, so this was the result which was received in the simulation. So as you can see, the bullet just pierced inside and came out from the other side, as well as there was no crack propagation. So this was for the failure strain, what was calculated. But when the failure strain was reduced, so this photograph is for 1/10 of the failure criteria which was calculated, and this is 1/100 of the failure criteria which was selected. So as we can see that in 1/100 of the failure criteria, it gave us a good correlation. So we wanted to know like what is exactly happening, like what should be the failure criteria that should be chosen. So that formed the basis of my work, like how does the dynamics of the glass material works, like what material parameters should be chosen. So that brings us to the dynamics of glass model. So glass is a brittle material, as well as there is negligible expansion when there is a tensile loading coming onto the sample, as well as it is governed by hydrostatic pressure, and this has been used for armor development because it has a very good high strength to mass ratio. So now I'll talk about like how the crack is propagating in glass. So what happens is suppose this is a glass. So if there is a bullet impact on this glass, so there is a compressive wave which is formed and which moves in radial direction throughout the throughout the body of the glass element. So if this compressive wave is stronger than the dynamic strength of material, then what happens is as the wave propagates, it kind of fractures the material and it keeps on moving. So as you can see from the photograph, there is radial cracks and it keeps on propagating. So we get a concentric radial circle failure as it moves around. But if the compressive wave strength is less than the dynamic strength of material, then what happens is if this impact glass, so there is a setup. So if this glass impactor strikes this glass target, so there is a compressive wave as shown in here is formed and it moves in this glass. And as it is reached this surface, it rebounds back as a tensile wave. And there is a sprawl plane in which the tensile force is developed. So when this tensile force is above 70 MPa, there is a failure in that plane. And what happens is now the surrounding element, whichever is there, is governed by this failure criteria of material, which is 70 MPa, and it keeps on cracking and propagates throughout the material. So this is what happens if the compressive wave is less than the dynamic strength of material. Next. So I picked up the result from Sandesh Gandhi's report, and I found that it was showing a very beautiful feature what was observed in the dynamics of material as well. And I would say that they did a really great job in finalizing the mesh pattern and the mesh size. So this is how it looked if there is a bullet impact and it moved radially. So I looked into like why material card is important. So what has happened here is, so there was a test which was conducted, and this is the simulation which is conducted for the same kind of testing, and material card is being incorporated in this kind of test, which ensures that the material property is incorporated in this kind of test. So when a general material was taken, it kind of behaved in this format. But when the model, which actually captures all the behavior which is there for the material, it gave a good correlation between the actual testing and the simulation. So the model which was used in this work was Johnson-Cook model, and this has been really regarded as the work for any ballistic impacts. Next. So the simulation, so my work in simulation has been done in Hypermesh and LS-DYNA. So all the pre-processing is done in Hypermesh, and the post-processing is done in LS-DYNA. So the way LS-DYNA work is based on material card. So what material card does is it kind of says like this is the material property which is to be incorporated in the model. So I went on to deciding on like which material card would be the best to take in consideration all the requirement of our testing. So what we did is, so LS-DYNA has around 294 material cards. So what we did is we found out the material card which is strain rate dependent, then which strain rate dependent card is based on Johnson-Cook model, and which Johnson-Cook model is based on glass model, and then which this gave us the model which would best take into scenario what is happening in our case. Next. So these were the 6 cards which takes into account these kind of behavior. So 032 was based on laminated glass, which is used in our cars for the simulation in our cars, a cars window. 60 was taken for high temperature forming. Material 110 is the material card which is best for us. 241 was the older version of it. Material 110 is the new version of it. 241 is used for taking into consideration the Bauschinger effect, which is like tensile loading and compressive loading, like cyclic loading of it. And 280 was not based on strain rate card. So now I'll talk about like why 110 is best suited for us. So 110 card, which is Johnson-Holmquist card, was developed specifically for this purpose, for taking into consideration the ceramics, if there is a ballistic impact on ceramics. So, so what it takes into account is the strain rate effect. The failure of the material is based on the failed material around it, so it makes it less mesh intensive. The tension is handled differently from the compressive strength, as we have seen in the dynamics of material. Like the tensile strength is different from the compressive strength, as well as the card makes sure that the element position plays a role in the simulation. So this card was best suited for our case. So the methodology which was chosen for our for this kind of development was that the simplified model and mesh pattern size, a good work was done before it. So we have a good simulation model. So based on the testing, we would have a framework of material failure criteria, which would be fed in the model what we have, and that would give us a good result. So this is the whole ideology, or this is the whole idea of this project. So instead of incorporating the material model directly into the model, it might take into account a lot of things, lot of parameters which we cannot account for. So what was done instead is that the testing separate apparatus was simulated so that we don't have a lot of variables, and it simplifies our material model. So based on this material model definition, we'll feed that into the old model and we'll get a good correlation. So this is the methodology which is followed in this research. So now we'll go on to the experimental results. So, so what is basically strain rate? So what happens is, if there is a car accident or sportsmen who go into like contact sports or something, so the loading which comes into play in this kind of scenario is strain rate model. So a lot of apparatus is there which kind of does the experimental testing, and this is based on the strain rate which it takes into account. So servo hydraulic machine is used for 10 to the power minus 6 to 10 to the power 0. Specialized machine or changes in the split Hopkinson test is used for 10 to the power 0 to 10 to the power 2. Split Hopkinson test is best suited for the testing in 10 to the power 2 to 10 to the power 4, and plate impact is used for doing the testing for strain rate above 10 to the power 6. So for the ballistic impact, the strain rate which comes into play is in the range of 10 to the power 6. Next. So this is also, we have selected split Hopkinson test for our testing, and this is how the schematics of the split Hopkinson pressure test look like. So what happens is, a striker bar is there, it strikes the incident bar, and there is a sample and there is a transmission bar. So I will show you like what exactly happens. So this is the animation from my simulation, and this is how it begins. So what is happening basically is that there is so when the striker bar strikes the incident bar, so there is a compressive wave which is formed, which moves in the sample, which is called the loading curve as well. And there is a strain gauge which calculates the strain which is coming, which is the loading curve. And when it impacts the sample, some of the wave is transmitted and some of the wave is reflected back. And based on the analysis of these three curves, we get an idea like how the test was conducted and what kind of stress and strain came into the sample. It's not. Can you escape and try? So this is how it looks like. So the compression wave is formed, and when it impacts, so the compressive wave is formed, and when it impacts the sample, there is some of the wave which is reflected back and some of the wave which is transmitted. So this is how the split Hopkinson test is going on. This is what is actually happening. Thanks. So these are the wave which we get from the strain gauge. So the orange one is the incident bar pulse, and the teal is the transmission bar pulse. And based on the analysis of these three pulses, we get, and these are the governing equations which comes into play. And based on the analysis of these three curves, we get this. So we get these kind of four curves. So strain versus time graph, stress versus time graph, strain rate versus time graph, and stress versus strain. And we have one of the best setup for split Hopkinson test in our MEME facility. So I have used MEME 702 test setup split Hopkinson pressure bar test for my testing. So the whole methodology of doing the experimental test was based on this. So I tried to find out that if we have any borosilicate glass testing results for from any literature. So what I found out that there were very little literature on that. So to have a good knowledge of that we are doing the test correctly. So what I did is, first of all, we conducted the test on steel samples, which had like a very good literature of what would happen if there is a split Hopkinson test carried out. So what it helped us doing is it validated our test methods as well as analysis that needs to be carried out and the experimental setup, how it has to be done. So it gave us a good idea of like how exactly we should be doing the split Hopkinson test. And then the learning from the steel samples were carried out for the glass samples. And then it was correlated for the, the result for the glass sample was correlated with the similar class of material to see that if we are getting a good credible result. Next. So let's start with the test result for glass samples. So this is how the setup looks like. So what we have done is we have taken 1018 cold rolled steel. The test separators is split Hopkinson pressure bar test. We have taken the same size of the dimension of the sample, what was used in the glass sample, because it would give us one less variable to deal with. So the input parameter which comes into play in this testing is pressure. So by changing the pressure, we are able to change the velocity of the striker bar, which determines the loading curve of the testing. The striker length was chosen as 9-inch. We kept it constant to reduce any other variable. And the sample which the number of samples which we tested was 2 samples each. Thanks. So when the test is carried out, so we get a sample after the testing. So what was done is we measured the length, the change in the length for the sample, and this is how the longitudinal strain looked like. So by looking at the strain, what we found out that for pressure less than 40 psi, we get a strain of less than 1%. And for this, for pressure above 40 psi, which is from 40 to 70, we got a strain of 2 to 5%. So that result was tested for. So that result was compared for the analysis result what we get from the experimental setup, and we found that it very closely related to that. So we saw that the average strain was increasing with increase in pressure as expected, and the strain was less than 1% for 40 psi and 2 to 4% for pressure in 40 to 70 psi. So average stress has to be taken for analysis. And with the increase in pressure, there was a significant increase in the average strain rate as well. So then this result was compared to the result what we have from the literature, and what we found out that we were able to match up the result what is there in this yellow segment. So the strain rate which was possible by these pressure change came out to be 700 per second. So we were able to simulate this small region. But the split Hopkinson test has a potential of checking the strain rate for this box. So what was suggested in that paper was that maybe we can change the L/D ratio, and by that we can get a strain rate higher without changing a lot of in pressure. Next. So after having a good understanding of like how the test is performing, after having a good understanding of like how to analyze the result, the same tests were carried out for the glass samples. So so same setup was used, everything was same. The parameter which was changed for this setup was the pressure, which was changed from 10 to 50 psi, and everything was kept same. So these were the result which we got from the testing result. So these are the average stress, the average strain, and the strain rate. So what we found out that all these sample broke when the test was carried out, as well as the strain which came onto the sample was in the range of 1 to 2%. There was, as you can see, that there is an constant increase in the average stress as we increase the pressure, as we increase the strain rate. And the strain rate which were observed in the sample was in the range of 100 to 250. So we failed to have a big range of split Hopkinson test, which might be possible for our split Hopkinson test. So there was some of the constraints with the number of samples which we can obtain. So we kept this result and we move forward. Next. So this is how the result look like. So this is the average stress versus strain rate curve. And as you can see, there is a good correlation between the average stress and the strain rate. And this is how it looks in the logarithmic scales. So since it's a brittle, so since this glass is a brittle material, so we were not sure like if the two samples what we have is a good representative of this study. So what we did is we took 7 tests under the same pressure criteria, and we calculated the average stress, average strain, and the strain rate. And these were all plotted. So we found out the same kind of result, that the average strain, the sample in the strain in the sample were coming out in the range of 1 to 2%, and most of this sample strain rate was in the range of 115 to 250. So if we plot those values, what we found out was this. So 4 values were in very close correlation, but these 3 values were outliers. So the reason which might have impacted this test was that if we consider this as the incident bar and this as the reflected bar, so if there is a non-parallel phase in the sample, what will happen is if this would have been a metal, there would have been a localized deformation and it would have taken that in account. But since it is a brittle material, what will happen is there would be a stress flowing from that region and there would be a crack propagating. So that would give us a less stress developed in the sample. And that might be the reason for giving us this outlier results. So I think if we can incorporate high-speed camera correlation into it, so that we see like how the crack is propagating, we might have like a good understanding of which data is good and which data is not good. So that could be incorporated to give us a good result. So after doing this testing, after having a good understanding of the test, all the data were collected, and this is the average stress, average strain, and the average maximum strain rate which came into picture. So the graph was plotted based on this. So the graph was plotted based on this. So this is the average stress versus average strain rate. As you can see, there is a good response of increase in strain rate with average stress. So this test result was compared to the literature what we have for the testing. So this is the result for the silica flowed glass. So what we can see in this graph is that this is how they have predicted that the stress would be changing with the change in strain rate. So the range we are talking about is the 2 parallel lines. So this is the range which we have, and as we can see that there is a good correlation between the change in strain rate with dynamic increase in the dynamic stress increase. So that is kind of captured in this result as well, and I think we were able to have like a good result for this simulation. Next. So now I'll talk about like what simulation work we did. So this is how the test looked like in 3 different scenarios. So the first one is the actual testing. First, let's say. So this is how it looks in. So it cannot be visualized. So the test is so fast. I just wanted to give you an idea like how the test is going. The test is going so fast. Now we'll see like how does it move. So we'll see how it looks in high-speed camera. Okay. This guy would also speak here. So this is how it looks if there is a high-speed camera correlation. And our simulation was able to capture this behavior. Can you play this? So in the middle, there is a sample. And this is the incident bar and this is the transmitted bar. So it kind of captured the behavior which was generally observed in the split Hopkinson pressure bar test. So the methodology which was adopted for the simulation work was that first we'll model the split Hopkinson pressure bar test, the same setup in LS-DYNA hypermesh. Then like the way the experimental setup calculates, like it takes into account the strain gauge. So the methodology of calculation was decided. The analysis of loading curve was kept done so that we have like a good understanding, like if we are able to reciprocate the same, if we are able to correlate the same result what we have from the experimental to simulation, and then the analysis of sample were carried out. So this is how the schematics of the split Hopkinson pressure bar test looks like. So this is striker bar, incident bar, the strain gauge. There is a sample in the middle, and the incident bar in the transmitted bar. And this is how it looks in the simulation. So what we did is we took the striker bar, the incident bar, and there is a sample in the middle, and strain gauge location is position, and this is the transmission bar. So the cards which we incorporated into our simulation was that the way we kind of took into consideration what is actually happening in the experiment was that we gave the velocity to all the nodes of the striker bar to kind of correlate with the striker things which is happening. This is so gravity is implied to all the setup, but since the test is so fast, so gravity doesn't play a very big role in this. The contact which was taken was automatic surface to surface contact between the striker bar to incident bar to sample, and sample to transmission bar. And the material model which was selected for the bars was 003, because we are not expecting any plastic strain to be happening in that bar. Hopefully it didn't happen also. Next. And this is the position of the strain bar position, strain gauge position. So the way we carried out the strain gauge analysis was next. So what we did is we identified like what is the area which the strain gauge occupies, and we took the stress from the elements around that area. And this is the positioning of the strain gauge. And as we can see, what we did is based on the deformation between the point A and B, we could calculate like what is the strain that is coming onto the sample. What is the strain which is coming onto the bar, which is calculated in the experimental result. Next. So this is the result what we got from the split Hopkinson pressure bar test. If there is no sample, these all calculation which goes behind it. So I'll not go into detail for this, but this is what we do. So next. So what we do is we have like a voltage versus time curve for the strain gauge, and this is converted to the stress versus time curve. Next. The same methodology was adopted for the simulation results as well. So we have the strain versus time curve, and this value was converted to stress versus time curve. Next. And now we superimpose the two results. So as you can see that we are getting a very good correlation in the time axis, like it kind of superimposed very nicely. And it was very improbable that we were getting, it was very improbable to get the same kind of result for the transmission bar, but we got a very good result. And we have an idea like how the loading curve is coming, so that we can understand like how will it impact the sample results. So this is how it looks. It had a difference of 20%. This is the transmission bar result, and this is the incident bar result. So we wanted to make sure that mesh is not the issue that is creating the difference in the loading curve, what we saw in the last slide. So what we did is we did the mesh consistency study. So initially the mesh size was 2.3, so we reduced it to 1.9 and 1.5, and same method was used of superimposing the graph. So this is what we found out. So we found out that there was no difference in the result. So it means that the mesh what we have is 2.3 is sufficient to categorize the result what we have. And as we can, and we went on for using 2.3 millimeter mesh size. So after having a good understanding of like how the loading curve is behaving, what we wanted to do is we wanted to move forward with the analysis of samples. So what we did is we found out the material model of which is used in 110, and these 5 ceramics were used, which is from the family of the ceramics which we are using. So what I also found out that the glass material which we are trying to simulate is one of the difficult one to simulate, because it has like 19 constant, as well as if there is a slight width, and it is very much parameter sensitive. So if there is a slight change in the parameter, there will be a huge impact in the results. So what we did is we tested the sample, and as we have seen in the experimental setup that it always broke, and we were kind of able to have the same behavior for the simulation as well. So it kind of cracked like this. So the simulation was carried out for these 5 materials. So what we found was the maximum stress and the average stress. And this is how the loading in the sample looked like. So this curve is for the silicon carbide. This is for 15 pressure, 25 pressure, 30 pressure. So what I mean by pressure is like the input velocity which comes into play. And this is what simulation result we were getting. So if we plot that curve in our result, so this is the experimental result what we got, and this is the simulation result what we got for different pressure. So the expectation was that we'll get some parallel lines for the testing, but it didn't give us the result what we were expecting. What it gave us was that these kind of curves. So it was kind of question like what exactly what could have been carried out to give us a good correlation. So it kind of is like what needs to be incorporated in the testing and the simulation side to have a good correlation. Next. So the model 110 is developed for the ballistic impact. So it kind of is best if designed in this region. So I think the data which we obtained, which was in this region, if we are able to incorporate the result from this region, we'll be having a good correlation. And this is what would be expected in the ballistic impacts as well. So the way we can do it, as we have seen, is by changing the L/D ratio. Maybe if we have if we have the image correlation by having high-speed camera, we had a good correlation, as well as determining the sample size, which should be there, so that we have a good data and a good understanding of like what data is doing. The factors which can be incorporated in the simulation is that we need to understand like how the material model parameters is changing, like how the result is changing with respect to the material with the change in the material model parameter. The study should be carried out to. So a lot of people suggested that if we incorporate shim, they were able to have like a good correlation between the loading curve from the testing and the simulation. So maybe shim study could also be carried out to incorporate to have like a better correlation in loading curve. So what was happening is that when we were doing the testing, we were getting for a same loading curve, we were getting like 10,000 results for the analysis of data, but the simulation was only having 10 data. We tried to incorporate the different method to reduce this time step, but we were not able to do it. I think like LS-DYNA works in a very different way. It chooses its own time step and it is not able to incorporate that. So maybe different softwares could be incorporated for capturing those kind of time step study. As well as some of the papers suggested that maybe we can cross development would be a good result, as in like we should conduct the experiment, we should try to match up with simulation, and then the simulation result should be matched with experiment. So together development was predicted for these kind of models. So on the whole, this was the achievement of my product for my project. So I was able to incorporate the dynamics of material, experimental analysis, and the simulation result. So the work which I did is able to have like a framework, like if there is a ballistic impact, like how exactly can we do testing and how can we incorporate the simulation work into it. So it provides a cheaper method of incorporating the material model into our simulation model. So if the countermeasure comes in the form of like if we have to change the material, maybe this model could be easily incorporated and it would give us a good result. So what we need to do is we need to just conduct test in split Hopkinson test, try to simulate that thing in simulation, and we'll get a material model which can be fed into the simulation result of the actual model. And as well as if there is a countermeasure in the form of maybe in change of material or how to optimize the mesh flow and all. So this could easily be incorporated by having the material model which I have developed. So it basically gives like if we have the material model, do the testing, put the simulation model in play, and find out the material model. So this is what I have achieved in my project. So at the end, I would like to thank the previous work people, that is Sandesh Gandhi and Vijay. They have put a really good effort in documenting everything. So I was able to start the project very nicely. I'd like to thank Matt, who helped me understand like how should I do the testing and all. I'd like to thank Omkar with helping me out for the simulation work and my FA team as well. I'd like to thank Arvind, who had to go through who had to read all my thesis as well as give me a good feedback on my simulation work. So this is how my team looked like. I'm really indebted to my team for helping me out in my work, as well as we had good time doing this project. So what's next? So I've been working with one of my idea, and if my committee decides me to pass on, so I'll be working on this idea, and I'm thinking of developing a product. So I'm working on a startup idea, and I'm thinking of developing this idea. So thank you, and I'm open for questions.
So with this part of the presentation, this questions are up to the audience. So ask really hard questions if you want. If you want to get revenge on Mayank for something he's done to you, now's your chance.
Yes.
I actually have two questions.
Mm-hmm.
So the first one is, what do you need by L by D ratio, and how does it affect your experiment itself?
So that's a very good question. So what happens is, so the sample size which we have taken is 0.3 in diameter and 0.3 in length. So what we were initially trying to do is that we were increasing the input pressure, which is like the striker velocity, and we're trying to have like so we were expecting that the strain would increase and we'll get the result for that. But what ended up happening is like the strain rate was not going at the same fast pace. So I go back to the literature, like what exactly, like how people have achieved for these high strain rates. So what I found out that if we reduce the length, it gave us a good strain rate study. So for the same impact velocity, if we reduce the length to half, the strain rate would come onto the material like in a higher magnitude, and we can have like a better as in like we can cover the whole bandwidth of the split Hopkinson setup. Yes. Did I answer your question?
Yes.
Okay.
So I don't know if this question is from your thesis or not, but the question I have is, so do you mean that if you increase the pressure inside a borosilicate glass, it will lead into less splitting of the glass if there is any ballistic impact?
Okay.
So is that the meaning of your thesis?
That's a very good question. I should have addressed that thing in my presentation, but I kind of did not address it. So the whole idea of US Bureau of Reclamation was that if we increase the pressure, then maybe we are able to fragment the glass more nicely. So what would happen is if we have like a smaller particles, so that would not impact the surrounding elements. So one of the countermeasure which was suggested by USBR, and the reason for them to conduct this 100 psi test was that if we increase the inside pressure, we saw that there were a lot of cracks. So if we can pulverize the glass into very small pieces, then it won't hamper the surrounding elements. So that was the whole idea of like incorporating the higher pressure into that testing.
So you mostly like went through the experiment with the material 110, right?
Yes.
And you tested also with other ceramics. So what like advantages you find about the 110 material? Like how is it like better than, because most of your experiment basis was based on the material 110, right?
So I think I have not clearly addressed that. So what I have basically done is that I have conducted the test for just borosilicate glass, and I have done the simulation for different kind of ceramics. So I was expecting that I could have the material model constants for borosilicate glass, but I did not have those kind of constants. So instead of developing a material constant, which would take into account a lot of testing, like we have to do impact testing, we have to do hydrostatic pressure testing. So there has to be a lot of testing that needs to be conducted for getting the material model for the whole borosilicate glass. And if the countermeasure needs to incorporate by changing the material, we again have to do for the newer material. So what I thought would make sense in my research was that we'll do the testing for borosilicate glass, and we'll do the simulation for other class of ceramics. So what it will help is what would provide is that we'll be able to capture the nature of capture the nature of material dynamics which is happening in the model, and we'll be able to approximate the material. So in a way, we won't be spending a lot of money in developing the material model for borosilicate glass, but we can approximate take into consideration all the nature or the dynamics of the ceramics. Did I answer your question? Yes.
I have another one.
Yes.
And like you say, like tested like a few samples, like of same sample for like a lot of times and find out there are a few outliers in the curve, right? Did you later find out like what are like why the outliers are caused?
I would say that I was not able to find out like why these outliers were there, but I went on through some of the literatures, and what literature suggested is that maybe there might be I think I kind of like addressed that thing. So I might have not explained properly. So what was happening is if the phases of the the whole split optical pressure bar test runs in the basis of that there should be a 1D stress flow. But if in case if the sample is inclined on one side, so what will happen is the bar would strike not for the whole surface but on the one of the surface, and there would be localized strain which would be coming onto that plane. But if this would have been a metal, it would have taken the strain and there would have been a localized compression in the curve. But in case if it is not there, or maybe this is what is happening for the glass, is that the crack starts propagating from there, and there is a and there is less stress which is developed in the sample, and then less stress is being calculated from the strain gauge data. So what paper have suggested is that we might have like a good image correlation. So what it does is it will give us like how the crack is propagating, and we'll have an idea like is this sample a good sample, or if this sample is not a good sample result. Did I answer it?
I have two questions. You can answer them in tandem. First of all, what is a SHPB study? I think you used the word.
Okay.
Second of all, you said that your samples in your experiments, all of them cracked, and that was so. Was there any? Do you think there would be any advantages in studying any of the samples like without cracking, like putting a low enough pressure on them so they didn't crack, or is that in a range that's so different from cracked glass that it's not worth using those results?
Okay, so I see what you're asking. So first I'll start with the SHPB study. So the whole idea of using the SHPB in split Hopkinson pressure bar test is that we want the sample to have like a uniform loading on to the sample, uniform 1D loading into the sample. So what it does is if we have, so what is meant by SHPB is that we placed a metal between the incident bar and the sample. So what happens is kind of like it creates a pressure in the it creates a uniform loading for the sample. So that is what was developed, what was done for the SHPB. So I did conduct some testing with SHPB. So what I found out that some of the material nature was coming onto the plane. So I used mild steel for my SHPB, and what I found out that the result was giving me a metallic behavior, which was not expected because we have a borosilicate glass which is ceramic. So I looked into the paper, how exactly they are doing it. So what they say is that they kind of see what is happening. They kind of correlate like how the experimental setup is behaving and how the simulation is behaving, and they try to match up with like putting on the SHPB and like doing that analysis. So this is your SHPB question. The second question what you had was?
All your samples that you tested in they all cracked, and you tested them for cracking. But was there any advantage in kind of putting some samples which did not crack, putting a low enough pressure that they did not crack, or is that completely different? It has completely different like mathematics that won't be useful in a crack.
Okay, so the way the material model is developed is that there is a hydrostatic pressure for brittle materials. So the whole idea of that hydrostatic pressure is we look into this the pressure which is being developed in the sample just before the failure. So that study is being used for developing the material model. So what was happening is if I would have gone for a lower pressure in split Hopkinson pressure bar test, so I was getting the failure or cracks and the breaking of glass sample for below 10 for above 20 psi. But and what was observed in the glass testing was when I used 10 psi pressure, I was not getting a good correlation. So what it might suggest is that 10 psi is not a good study, or the sample size combination and the 10 psi would not give us a good conclusive result. So I did not go below it, which might have been the case when the sample would not break. So this is what happened. Did I answer you?
Yeah.
So can you help me to understand how the striking of a bar to the sample is same as striking with a bullet?
Okay, that's a very good question. So what happens basically, so how is this related? Like how the bullet impact and the test which we are conducting is related. So what happens is that when there is a bullet impact, there is a compression wave which is formed and which goes into the material. So the same kind of nature is being tested with the split Hopkinson test also. So there is a compression wave which goes through the sample, and we can calculate like how is it behaving for different loading and different kind of stress versus strain graph we are getting from there. So it kind of is a laboratory testing of what would be happening for the strain rates which is coming to the class. But definitely the ballistic impacts has a strain rate of 10 to the power 5 to 10 to the power 6, but split Hopkinson gave us the result for 10 to the power 2 to 10 to the power 4 per second. But the result of this split Hopkinson test could be extrapolated to the ballistic impacts, and this gives us a good result. Impact test is used generally for higher strain rate, but the extrapolation of split Hopkinson test also gives us a good result. Did I answer you?
Yeah.
Mm-hmm.
I have a couple of questions.
Mm-hmm.
So you did the test on it being 0 degree impact, so the bullet or the pressure wave was impacting it at a 0 degree angle. Were you also thinking about having a different angle parameters because 0 degree is not always ideal in real life?
Okay. Yeah, that's a very good question. So what basically happens is in split, so by 0 degree you mean that the incident bar is striking in a different angle?
Normal.
Okay, so the bullet you mean, right? You mean the bullet?
That's my second part question. So it's in the Hopkinson's pattern setup, where was the wave that was generated in the sample given in a very small area, or was the area distributed, like the impact on the sample where, like, what was the pressure on the sample? Was it like as minute and small as we have in ballistic? Because ballistic contact is very, like, it varies with different whatever ballistic we are using, but it's still very small compared to whatever pressure you are giving. So are you giving it very small, or is it like is it spreading through it with having a larger diameter?
Okay, so I see what you're asking, and I'm not sure if I'll be able to address, but I'll try. So what is happening basically is, so split Hopkinson test is used for doing a 1D analysis. Like we assume that there is a 1D flow in the stress, and that gives us the result of like what is exactly happening. And if this condition is not fulfilled, then it does not give us a good result. So the test setup kind of gives us the nature of the behavior in 1D, but it gives us a good correlation of like how will it behave in 3D as well. So now coming back to the setup, what we have in the original model is a 3D. And obviously, if there is an incline in the bullet, there would be a different scenario which would come up. But what I feel, we have not tested it, but what I feel is that if we have incorporated a good material behavior, which is kind of like a 3D behavior, like how will it behave and all, so that can give us a good correlation. And researcher has found out, like some of the work has found out that when these metal models were incorporated in their analysis, they gave us good results. So what I'm expecting is that the testing result, the 1D testing result, what we got, can be correlated with the 3D result, and it gave us a good correlation. So I would say like the result obtained for 1D is good enough for incorporating in the 3D. And this would be the growth if the project is taken forward, this would be the direction I suggest would be going forward.
So I have one more question. So in the beginning of your slides, you gave two animations on 0 psi and 100 psi. I couldn't understand what was the psi for, like the impact of the ballistic, or like I heard you said atomic pressure. Was it just the unit, or you actually were considering atomic, like atomic pressure, atmospheric pressure? So were you actually considering atmospheric pressure, or it was just a unit? And second part of the question is, I did not see in further of your slides things going to 100 psi. At max, I saw it was 60 or 60 psi. I want to know why.
Okay, so I kind of like I did not address it properly, I would say. So what was happening before is like for the USBR test setup, what was done is they built up an internal pressure inside the tube. So the whole idea of doing that internal pressure was that if there is an internal pressure, there was more cracks, which was observed, and that would give us good pulverization and it would not impact the surrounding element. So that was the pressure for the testing. But when the testing was conducted for different pressure, the whole idea was to change the impact velocity. That would change the loading curve and that would change the strain rate which is coming onto the sample. So I think like the pressure what we have for the testing in USBR testing and the testing data what we have for the split Hopkinson test is kind of different. So the whole purpose of using the pressure in USBR test was to see how it's behaving, and Omkar has been working on the simulation. Omkar is one of the guy who's working with my in my team. So he has been seeing like if there is an internal pressure in the tube, how will it behave, like how the crack is propagating. And if you look at the split Hopkinson test pressure, the whole idea was to change the impact velocity that would change the loading curve. Did I answer your question? So what I meant is like it's a different scenario. Like the pressure in split USBR testing was to incorporate the behavior if we have an internal pressure, and for this was to just change the impact velocity.
So both are different pressures.
Yes.
And did you see like take into account the inside pressure of material? I don't know if you are.
So the whole idea for that is that it should work in series. So what has to be done is that the pressure inside the tube has to be taken into consideration for FEA model, which was done for USBR. So Omkar is working on that. So he'll be doing that, but it would not impact the material model which is developed by split Hopkinson test. So it will take into account what is happening based on the material perspective, and the simulation cards has to be incorporated for incorporating the internal pressure.
One more silly
Yes.
question.
Mhm.
How did you achieve the L/D ratio? Like, did you cut the material or did you use the
So we had a constant in the material which we received. So I conducted the test just for 0.3 diameter and 0.3 length. But if we can reduce the size, like if we can reduce the length of the size, we can go for higher strain rate. So it was, so in case if this project is taken forward, this could be the step in which we can cover the whole range of split Hopkinson the wavelength, what can be done by split Hopkinson test.
So did you receive the specimen or did you cut it here? Like the ratio you said it was 0.3 by 0.3. So did you receive that sample as in, or did you decide the dimension?
Yeah. So what happened is so Chrissy has been helping us a lot. So she arranged the sample and she gave us the sample for this. So the sample for borosilicate glass was given by USBR, but we had a control for the 1018. So we tried to maintain the same kind of sample size so that we have one less parameter to deal with. So I would say that the glass sample was received from the USBR and the steel sample was in our hand.
When you did the experimental simulation, have you seen the literature someone doing using? You started off in the simulation with putting this the glass model, but did you try putting in the steel model to validate the simulation?
Yeah, so it's a very good question. So I was thinking of doing it, but I did not do it. Maybe that could be a very good method to validate like how my loading curve is behaving for the steel sample. And since I have the result for that as well, so that would be a good method, I would say, for validating the simulation. But the reason why I did not do that is that I wanted to validate the loading curve, which is going on to the impacting the sample. So I kind of did not want to go for the steel samples because again the material model of the steel samples comes into play and we are not sure like how exactly it's behaving. So the whole idea was to validate the loading curve which goes on to strike the sample, and then we went forward with it. But it could be definitely a good work to go for the steel sample which was tested.
So sorry. So I have this wee question. You have the graph on outliners, and you have another graph after that, which I think I saw it had the same x and y axis. but show different graph. If you could go to the slide, it would be a real big help because it was so quick. I think I saw it had the same X and Y axis. The one that had outline.
Oh, outlines. Yes.
Yeah, and the graph after that. These two, I think, have the, yeah, yes, I think they both have the same X and Y axis, but one had outliners, but the other didn't. Why would you say so?
Okay, so the whole idea of doing this test was to see like if we have the outliers, and this is how it behaves, the outliers. So what was done in the final data analysis was that whatever, and we saw that the data would somewhat be expected to come in this format. So whatever was not coming in these fitting criteria, we kind of so whatever value was not coming in this kind of scenario, we kind of neglected that, assuming that it's not a good result. It might not be a very good assumption, but I think like it's a one of the good assumption to move forward with.
The deviation is really good in this graph, but the deviation that you had in the earlier graph was way, like
This
you
one?
just circled one of them being good and the rest of them being bad. But it's the same graph. How is it different from the other? Like, why don't you have like? Do you have any good, like, why? What signifies the circle if it's just like here also it has outliers, and but you still have a linear graph showing that the rest of them are just some deviations from for your experimental value.
Mhm.
So why to have two different graphs with the same data, but one being one having some points being super good and the other being like a deviation graph?
I see what you're asking. So what exactly is happening is, so basically what happened is I kind of conducted the test and I found some of the outliers. So the whole idea was to see like why are we getting the outliers. So when I found out that okay, these were the outliers and it was not, and it had a significant difference between the trend line and the outliers. So what I thought was that maybe if we can conduct the test for the same pressure, for the same input condition, like what kind of curve we are getting, because maybe two samples is not a good deterministic study of the actual test. So what was based on these curve, what I did is I kind of conducted this kind of test. So it gave us like what exactly is happening, and as you can see that there were a lot, and if you see the axis is 540 to 640, but whereas this has the 0 to 640, so it might seem like it is being elaborated. So that might, I think, might be the reason why it looks so different from there and this one.
So what's the significance?
Can I interject real quick?
Yes.
This is Chrissy. So anyways, maybe you could shed some light on the probabilistic behavior of glass in the way that it has a large amount of probability in the results. Maybe you can talk about some of the material properties that make that an issue when you're testing glass samples.
Yeah, so yeah, definitely that's a very good way to explain this. So what Chris is trying to address is that material, glass is a very different kind of material with steel, because the internal, so so Dr. Morse gave a best definition of glass I could possibly imagine. So what he said is that glass is a kind of like a compact powder which is put together, and it is just waiting for an impact to happen to disintegrate into pieces. So what it means is that when it is being compacted into a small element, there might be defects which is there in the glass sample, and that might produce a site for going the damaged chrome. But that is not same for the metal testing. Like for metal testing, what happens is there's a localized deformation in that region, because it can take into localized deformation, and the impact of that kind of defects which is there in the metal won't be a lot. So, but in glass, as we can see, that there is a lot of value difference if this comes into play, if the defects in glass comes into play. So that is what I meant by this study. And did I address Tracy properly? Did I address?
Sorry. Yeah, I think that was a good explanation.
Okay, thank you. So did I answer your question? Okay.
Yeah.
Okay, so let's give him another hand. And so now I don't know if you need a 5-minute break or anything.
I'll take a break.
Okay, all right, so we'll transition to the closed door session of this, so thank you for coming. Thank you.
Somebody turn on the light.
We need to clear. We should do the screen right here.
Yes. Lots of tweets.
Oh, okay, all right, okay.